Chris, thank you, and everybody at the Vicksburg Club. Sorry, I couldn't be there tonight. Chris will fill you in a little later during the business meeting, but looks like we've got a pretty good crowd here in the radioactive on the River City. George Zafiropoulos is someone who's well known in a number of realms. George has been an executive with National Instruments for a good part of his career. National Instruments is a software company that if you buy products that get mass produced and they require a lot of testing before they leave the manufacturing bench, they were probably tested using National Instruments software. But not too many months ago or so, George retired and he and his wife moved to near Portland, where they had vacationed and decided, hey, we need to move here. And so I've gotten to know George over the years. I was a guest on the podcast that he co-founded called the Ham Radio Workbench podcast, and they were really hurting for good guests. So they got me to appear, and I was just a so-so guest talking about GPS discipline oscillators and how to make your test gear a little bit better, a little more accurate. George has had a company, and it's Sierra something or other. He can fill in the blanks there, but he developed controllers for repeaters. And if you're familiar with the Cactus Intertie, they were largely controlled by the repeaters that George had a direct hand in building and designing and selling, etc. Now, if you know the initials DMR, some people use that to say, well, that's George Zafiropoulos' initials, because he's always talking about DMR. And if you're on the podcast and listen to it, you know, they tend to go into DMR overload. Why? Because George knows an awful lot about DMR radio and is kind of a guru, and I've learned a lot from him. Tonight, he's not talking too much about that, but he's going to talk about something else that he's been doing for a long time, and that is hiking and taking a radio with him in portable operations. He hiked with some pretty decent folks. I mean, the two people that he shared field day with frequently, gosh, they started a company. You may know them as Elecraft. So he knows those guys personally and knows that company very well. So George is going to talk tonight to the club about portable antenna or wire antennas for portable use. And I can't say enough good things about George. If you don't listen to the Ham Radio Workbench, you are missing out. It's like gravy on your rice or mashed potatoes. You ain't getting the full effect if you don't have that. So let me encourage you, and let's start off with a round of applause for our guest, George. George, I'm going to turn it over to you and put myself on mute.
All righty, great. Thank you very much, Frank. Now my head is swelled so big, I'm surprised it fits in the screen, but that was very kind of you. And I have to say, we really appreciated you coming on the podcast because it raised the overall IQ of everybody participating. So that was really great. Good evening, everybody. Thanks for having me on as a guest. The topic of this talk that I'm going to give here is it's portable antennas. Think like a backpacker, and I'll explain what I mean by all that in a moment here. So before we dive into all this, I can see some of you guys in the meeting room. So how many of you are active or have ever done portable operating like SOTA, POTA, or field day? How many of you folks? Yeah, about half. Very good. And the rest of you are like, you know, maybe someday you might be interested in that. So I love portable operating. When I was a teenager, my favorite event was field day. And we used to go out with old radios and generators and all kinds of heavy duty gear. And of course, that's all changed now because everything is so small and lightweight. And so I'm going to focus on very lightweight kind of portable field operating. And in particular, a bunch of antennas that I designed that I was really looking for super lightweight antennas, and I was never happy with what I found. And so I just designed my own and started making them. And so I created a little company called Pactenna, and that's available, you know, on the web. You can go find Pactenna and buy antennas from us. And everything I'm going to talk about here is basically the journey I went through in discovering what kind of antennas I wanted and how to build them, and share with you the designs. All of the antennas that I make, you can make yourself if you are a hands-on kind of person. So you can certainly make them. There's nothing secret about these kind of antennas. We just happen to make them for folks if they don't want to bother doing it themselves. So let me go ahead and share my screen. Okay, so hopefully you can see the full screen there, the big orange slide. So can everybody see it okay? Yeah, good. All right, thank you.
Yes.
All right, so 2 quick slides about me, as if what Frank said wasn't enough, but I've been licensed for a while. Got my novice back in 1972, and I've been licensed ever since then. I have a variety of interests in amateur radio. Portable operating has always been high on my list. Building stuff, kit building, stuff I designed. I do a lot of repeater building, as Frank said. So really kind of more DIY. I'm the guy who will build a radio, make 2 contacts, declare victory, and move on to the next project. So I'm not the 500 QSOs in a weekend guy. I'm kind of the builder type. What you see on the left-hand side at the bottom there is my first station back in 1972, over 50 years ago. Hard to imagine. Was a Drake R4B, which was a fabulous radio at the time and not too bad today, and a Johnson Viking Ranger 75-watt CW AM transmitter that was my novice transmitter. And that thing weighed an absolute ton. But you know, you get what you can get when you're a teenager, and you're really fortunate you can find anything to actually buy. On the right-hand side is more to the modern station today. The main radio here is a Flex 6400 and a Elecraft K4 for my main station. And then I got a whole bunch of portable radios, too numerous to list. It's kind of a mania, but I really love playing with various radios and learning the intricacies, figuring out which ones I like, which ones I don't like. Everybody has different opinion, and so it's a very personal decision. So whenever you ask advice like what radio should I get, you know, always take the answers with a grain of salt, because what may be right for one person may not be right for you. And so it's fun to play around with a lot of different gear. As Frank mentioned, I have a podcast called the Ham Radio Workbench. We started this back in 2016. My buddy Jeremy, KF7IJZ, and I started it, and he was with me for 100 episodes, and then went off to do other stuff. And now I have a team of other people working with me for the last 100 plus episodes. So we're up to number 204. And we publish an episode every 2 weeks. They're about 2 hours long on the average. We rarely go less than that, and they're often peaking up about 3 hours worth of content. It's a very hands-on-y kind of thing for people who like to build and like to understand technical stuff around radio. And we just have a great time. So we have a really great crew of folks. So please check that out. You can see it at our website, hamradioworkbench.com, or you can get it on your phone or your tablet. It's on every podcast player. Okay, so let's talk about building antennas. And remember, the whole theme here is building very lightweight portable antennas. And I wanted, just for my own use, I wanted some kind of very portable antenna system for HF operating for a variety of reasons. I love field day. I like to go backpacking. I used to do a lot more of that when I was younger, but I still occasionally do that. A lot of car camping. I like to go to the park to operate. And if I travel, sometimes I like to take radios with me, but I don't really want to make that be the main luggage. I just want it to be a small extra thing I take. So in all of these pursuits, size and weight are really paramount. That's a real big factor, because you know, big heavy antenna just gets in the way, especially if your main purpose of travel is not radio. If it's just for a vacation, you don't want it to take over. So you need something that's ultra light. So when I lived in the Bay Area, this is what my typical sort of POTA activation would look like. This is the Santa Cruz Mountains, and along the trail, conveniently, there's a park bench, so that was very nice. And I would set up my gear on the park bench, and this is a few years back. My main portable radio is a KX3 and a lithium iron phosphate battery and some accessories, and then some very thin coax running up to a end-fed half wave, partly supported by the hiking pole there. And then wire up into the tree. And that's the kind of antenna I typically use for portable operating eventually. Now, to get there, I went through kind of a long journey to find something very ultralight. And it started out with me buying practically every antenna I could find in search of the Holy Grail, which is a good performing, very lightweight HF antenna. And some of these things are, I'd say almost all of these are very well made. So they're all fine. Almost all of the manufacturers of these antennas make really high quality products mechanically, but they all have one thing in common, that is that they're really heavy and bulky, and they're just not appropriate for the kinds of needs that I have. The problem with a lot of portable HF antennas is to get them small enough to carry around, they tend to inductively load them to mechanically shorten the elements, which means that it will resonate, but it'll be relatively inefficient in order to get the size down. And so that's really a compromise. It's really a compromise if you're operating QRP of 5 or 10 watts. So I was just not happy with any of the portable antennas on the market. And even today, there's not a whole lot that I would say fill the bill. So this is what set me down the path of designing some newer, lighter weight antennas. So I had two inspirations behind the design of what ultimately became the Pactena antennas. The first is when we did field day, my very favorite field day antenna is a wire vertical, and we got a fiberglass pole that we would put up, run a wire up the side of the pole, and at the bottom of that pole we had a little plastic ammo can, and in that can is a SGC antenna tuner, and then we threw some radials out on the ground. And I absolutely love this antenna because you can work any band with it. You could put it together in a few minutes, and it was pretty easy to take down and pack up. So it's not like your typical big tower and a Yagi and all that sort of heavy duty stuff. It's very small and lightweight for a park kind of portable or a field day kind of activation. So there were some really good learnings in this antenna. One was the fiberglass pole was a super convenient mechanical support for the wire that was the radiating element. And in this case, with the antenna tuner, I could work any band. So that was kind of a nice combo. The second inspiration for coming up with really small, lightweight antennas is a book by this guy, Ryan Jordan. So he has a book that focuses around a lot of the philosophy of very lightweight hiking or backpacking. And he boils down his backpacking recommendations into a few basic ideas. And I thought these ideas are not just relevant to backpacking, they're very relevant to portable radio operating. So if you kind of run down through the list here, essentially remove everything you don't absolutely need. You know, trim away all the weight, plan out what you need, make sure you take the lightest possible materials, simplify the system as much as you can, make it interchangeable so it's a system, and don't make things more complicated than they need to be. These all seem like very good philosophical points to bear in mind when you're designing an antenna system for very lightweight and portable operation. By the way, as a backpacker, even when I was a teenager, I was the guy who would like cut the labels out of the back of my shirts to reduce the overall weight. So I'm a weight wimp. I really wanted to minimize weight regardless of what it is, and so there's no difference between, you know, your camp stove and your radio gear. So I set out with some goals in mind. One is that operating QRP, by definition, you're operating low power with these portable deployments, and a full-size antenna will be more efficient than an inductively loaded antenna. In other words, an antenna that's shortened with a coil in the middle will reduce the size, it'll be resonant, but it won't be as efficient. So a full-size antenna would be desirable. I want to use very lightweight components. I want to use hardware that is appropriate for field use. It has to be very modular, easy to set up, and I want the thing to be up and on the air in 5 minutes or less. So I'm lazy, I'll admit it. I don't really want to get there and spend an hour, you know, constructing some complicated antenna. I just want to get it up and on the air. And I want to be able to pull it down in even less than 5 minutes. So these were my initial thoughts and goals. So there's two big decisions that really drove the direction of the antenna design. The first is to use full-size wire elements. Full-size wire element, two important attributes there. Why full-size? Because they're more efficient and they're broader band. So they're also lighter weight because the only thing you have is wire and something to hold up the wire. So wire is super efficient as a radiator. It's very small and compact when you roll it all up. And so it's just great mechanically. The problem with wire is it doesn't hold itself up. So you have a challenge of how to get the antenna wire up and into the air. Now, a lot of people would say that's not a problem, just throw it in a tree. Well, if you're backpacking in the Sierras above about 8,000 feet, there aren't any trees to throw a wire into. You know, you're above tree line. And so there is no place to throw a antenna wire. And it turns out also, if you go to a lot of parks, you're not allowed to stake things in the ground or throw things in the tree. So that's kind of another factor. So you really can't rely on something there to hold up your antenna wire. Now, what really was a big enabler here is finding in the market a 32-foot fiberglass telescopic pole. So there have been a whole lot of poles made in the past for fishing, but a lot of these poles are about 12, 15 feet long. That would be fine for 20 meters, but I'd like to work 40. The money bands for portable operating are 20 meters in the daytime and 40 meters in the evening. So ideally, I want something that could support a 40-meter antenna. Well, when I found this 32.5-foot, when it's fully extended, fiberglass mast, I thought, oh, that's really interesting, because when you collapse it down, the whole thing collapses down to 26 inches long. So it was like, this is mind blowing. Before this, I found some fiberglass poles that would be long enough when extended, but when they collapse, they'd be down to like 3.5, 4 feet, which is just too inconvenient to carry. And those are largely used for things like wind socks and wind chimes. So this particular mast that I found was just a game changer. So those are the two key triggers that really set forward the path. So I figured, okay, decision one, use wire antennas. Decision two, you get a fiberglass pole that's 32 feet long. What would you do with that? Well, it turns out you could do just about anything you can imagine with it. So you could take that wire and make it into a variety of different kind of antennas. You can make a dipole, or essentially an inverted V with the mast holding it up, or you can make a ground plane on 20 meters. You can make a delta loop. You can make an end-fed sloper. You can make a vertical antenna. Just about everything you could think of, you could do with that material. So it means there's a whole lot of flexibility. This is a picture of the original Pactenna. This is no longer being manufactured, but what you can see here is the original version had a feed point. That's the white thing in the middle. So it has a balun in the feed point. So the BNC connector on the bottom is where you connect your feed line. And then the wires have loops and clips. So you clip the clips in the holes in the feed point, and then you have these little pigtail wires with banana connectors that slip into the banana sockets on the feed point. Now, this feed point has a whole bunch of banana sockets, and that enables you to build virtually any of these antenna configurations that you see here. So I use for the connectors 2mm gold banana plugs. The reason is that they're reasonably robust, but more importantly, they're fairly long contact between the barrel of the connector and the pin of the connector. So you get a lot of surface area, and that's important not only for just a general good RF connection, but in the field, if it gets dirty, there's still a fair bit of surface that's going to make a good contact. So this is the original link dipole design using 2mm wire and the larger feed point and some RG58 style coax. Now, since then, several years ago, we completely redesigned all this to make it even smaller and more compact. And that's what I'm going to show you in a moment here. You can see there the fiberglass mast on the left-hand side, 26 inches when it's all collapsed down. You pop that little cap off the end there, and up goes all of the 17 elements to give you a 32-foot mast if you deploy the whole thing. You can also unscrew the bottom, by the way, and pull segments out. So if you only want to do, let's say, 20 meters and you want 16 or 18 feet of mast, you can just take out half of the segments and just pack that, which makes it much lighter and even smaller. So this is what the current antennas look like today, and there's a variety of different antennas. What you see here are 3 feed points and a choke. The first one is the dipole feed point. This replaced the one you saw on the previous slide. And you can see all these antennas are designed in a figure kind of X shape, and that's to make the body of the antenna a wire winder, so you can wind up the antenna wire very conveniently. All of these antennas use 26 gauge steel wire that's copper coated and then insulated. So it's good antenna wire, but it's still very small and it's pretty stealthy, and it doesn't tangle up very easily. So there's the inverted V or dipole feed point first. Next to that is a random wire transformer, a 9-to-1 unun. which is my favorite antenna actually of all of these. And then the next one over is a end-fed half wave with a 49-to-1 transformer, so you can get away without using a tuner. The one in the middle, the 9-to-1 requires a tuner, and the dipole and the end-fed half wave do not. And then on the far right is a inline choke without the covering over it. The covering's been removed, and it's a simple 1-to-1 current balun choke, which is very handy when you're operating high power. I'll show you where that gets used in a moment here. Now, at this point, I get a pretty common question, which is, well, which antenna should I use? And my answer, for those of you who are golfers, you would appreciate this. The answer is this is analogous to someone saying, which golf club should I use? I'm going to buy one club. Which golf club should I buy? And the answer is, well, any golf club you buy will be useful for something, but it doesn't replace a bag of clubs. Why? Because they're all really optimized for different things. And you could play around a golf with 3 or 4 clubs, but it's pretty hard to play with one. So in the same way, if you look at all these different antennas, why are there different antennas? Well, they're kind of optimized for different things. You could be perfectly happy with one of these for all of your hamming needs, but there's some cases where you want different ones, and it may be based on the physical space you have, the amount of power you're running. There's a whole bunch of things you might factor into your decision making around which one. So most of the people who buy our antennas buy one and then usually come back for another and another, and eventually collect the whole set. So so when I go out, I take, if I'm going in a backpack with one radio, I'm probably taking my random wire with a KX2, for example. The random wire is the perfect fit for that. But if I'm going out to, let's say, a club outing where you never know what you're going to be doing, I just take all of them, because that way we can run multiple stations, have backups, and kind of get on the air no matter what circumstances we face. If you want to learn more about the PAC-10 antennas, we had a nice review in QST a few years back, and there's tons of videos on YouTube. So if you go on YouTube and just type PAC-10, you'll find like a zillion videos of people, not mine. I've never made a video actually to go on YouTube. These are all videos that other people made and put up on YouTube, and you can check them out there. Now, here's the other most common question. So what's the secret of the PAC-10? Why is it such a successful antenna? What's the magic behind the design? The answer is nothing. There is nothing magical about any of these antenna designs. Everything that I've shown you so far, you can go look up in the handbook. In fact, you can probably go back to 1939 and look up all these antennas in the handbook. There is nothing new electrically in these antenna designs. These are tried and true methods of building antennas for decades and decades. The only thing that is kind of novel is the way we manufacture them, and we just optimize them for parts quality and size, and that's really kind of our claim to fame. But the actual antennas themselves are not like some miracle invention that someone came up with, not at all. You could build them yourself. In fact, we often encourage people to do that. So if you want to have a good hands-on project, any of these antennas make great projects to build yourself, and all the instructions are on the web or they're in the handbook. Okay, let's talk a little bit about antenna theory. I think it's useful to understand how these antennas work. And there's a lot of mystery around some of these things. Most people understand what a dipole is and how a dipole works. And a dipole is basically a 2-element, hence the name di, a 2-element antenna where you have a quarter wave on either side and a feed point in the middle. And this is a resonant antenna. You don't need a antenna tuner, a matching unit of any sort. You should be able to run a 50 ohm coax from this antenna to your radio, and the radio should be pretty happy on the frequency that the antenna is cut for. If it's a full size wire, that range that the antenna is cut for could be most of the band. They're fairly broad band if you don't add a bunch of coils to it. So that's the nice thing about a dipole. They're very inexpensive. Everybody can make one. Everybody should make one, quite frankly. So a dipole is really great. Now, there's a downside to a dipole. Actually, there's sort of 2 downsides from a portable operating point of view. One downside is you have to hold it up at both ends, which is kind of impractical. Maybe one support in the middle, and you make an inverted V dipole, that's fine. The other downside is a true horizontal dipole, you really want to run that antenna at a half wavelength above the ground to get any kind of reasonable DX sort of range. as you lower that antenna towards the ground, it will start to bend the radiation angle from the horizon upwards. So the closer you bring it to the ground, the more upward your signal. Now, if your goal is to talk over to the next county, this is a good thing. If your goal is to talk to the next continent, it's not a good thing. So bear that in mind when it comes to these kind of horizontal antennas. But anyway, electrically, these antennas are very simple. Everybody can build one, and they work pretty well. Now, the configuration that we generally use in a dipole is something like this, with a fiberglass mast holding up the feed point, and then on either side you have a wire element, and that's an inverted V. You want to keep that angle between 90 and 120 degrees, and then you have a good inverted V antenna. And the way we make ours, we make them as a linked dipole, essentially linked inverted V. So you can have one element for 20 meters and a second element that gives you 40 meters, and you can connect and disconnect those points. You can make it any band that you want if you want to cut your own wire and just finish off the ends with the connectors. Very easy. You don't need a tuner, so they're really great antennas. Certainly one of my favorites, and it makes for a great home antenna too, if you want to put up a very simple, inexpensive antenna at home. When we make these, the wire elements, the way we do it is we finish them off with a loop that we snap on a plastic clip, and then there's a little piece of wire and a connector that dangle from that. So the actual strain on the wire is held by the clip and the wire itself. The connections are these little pigtails with a banana connector. That way we don't have any strain on the connection. This is a little prototype, so the little ferrule thingies here are longer than what you see. But these are the type of connectors we use. You can buy these at a hobby shop or on Amazon quite inexpensively. And so at the end of the wire, we solder them into the connector, and then we put heat shrink over that to provide a strain relief on that point where the wire is soldered to the connector. Here's another configuration. You could do something like a 20-meter ground plane with a 16-foot element going up as the vertical, and you could even use wires as your guys to hold the mast up if you like, and you can have a conventional ground plane. So it makes for a decent antenna. Okay, so now we're going to get into the easy stuff. We're going to talk a little bit about antenna theory. Now that we understand all about dipoles, right, the basic antenna, we're going to reference the dipole as we start to talk about some of these other more unusual antennas. So actually, there's no math involved, or at least very little, so not a problem. Let's talk a bit about our good old friend, the dipole. So a dipole, as I said, has a quarter wave on either side for the desired frequency. Turns out the feed point impedance of a half-wave dipole is not 50 ohms or 52 ohms, which we wish it were. It's about 71 or 72 ohms. And that's odd because we always think, well, I could use a dipole with some coax, and I just hook it up and it works. Why is that? It's because 72 ohms is pretty close to 50 ohms. Yeah, close enough. It's not such a high SWR, the transmitter will complain. And if you have any kind of tuner at all, it'll trim this and it'll be just fine. So this will work perfectly A-OK. So our reference antenna here is this half-wave dipole. Now, an end-fed antenna, which two of the antennas I was talking about are very commonly used in portable operating because they're mechanically more convenient to deploy. The end-fed implies that you're going to feed it from the end, not from the middle. So what happens to the impedance? If you were to construct this antenna by moving the feed point to one side, so the wires are still a half wavelength in total, but the feed point is maybe a third of the way into the wire, not in the middle. What starts to happen, you can see here, the impedance of that feed point starts to go up. The closer you get to the end of the wire, the higher the impedance. So it's going to go from about 72 ohms to up to several thousand ohms by the time you're feeding the antenna at the far end. So if you put the entire half-wave wire connected to the center of the coax, that feed point impedance is going to be somewhere between about 3,000 to 5,000 ohms, which is a far cry from 50 ohms. And if you put a 4,000 ohm impedance on your 50 ohm transmitter, it's not going to work very well. It's definitely going to complain. It's going to be a very high SWR, and you can't use it. So how do we solve this problem? The way we solve the problem is we have to bring down the impedance. And also there's another problem we've created. What happened to the ground side of my antenna? Half of the antenna just disappeared. How is that going to work? So what even happens at that point? Well, bringing down the impedance is easy. We use a transformer to do that. But what about the counterpoise? And we'll get into that in a moment. Okay. So here's a little diagram of your radio out in the field on the picnic bench. And let's take, for example, the end-fed random wire in our example here. So what you've got is a piece of coax that goes from the radio to that feed point. And then from the feed point, you have a wire, which is the actual radiating element that goes up into a tree or a pole or something. In the case of the end-fed random wire, it is by definition a non-resonant antenna, meaning it's not resonant at the frequencies you intend to operate at. It will be resonant somewhere, but you're designing it specifically to not be resonant where you want it to operate. And there is a transformer in that feed point, in that little blue bubble there, that allows you to transform whatever impedance is at the antenna at a given frequency down at a 9-to-1 ratio. So we'll talk about how that works here in a sec. The actual wire lengths, you can put, you might say, well, okay, random wire, I could put any length of wire. Well, not exactly, because what you want to do is you want to avoid a half wavelength on any frequency you might be operating on, or any band. Let's make it simple. So there's some conventional lengths, conventional wisdom you could use. 29 feet, 35 feet, 41 feet, 58 feet, 71 feet. Any of those lengths will work fine as the random wire length. Why are those magical numbers? Because if you calculate a half wavelength at 80 meters, 40 meters, 20 meters, 15 and 10, all the bands, none of those lengths are a half wavelength at any of those bands, which means it's a good antenna for any of those bands if you have a tuner. Now, why are we trying to avoid a half wavelength? Remember what I said on the previous slide, that a half wavelength feed point impedance is very, very high. It's like 4,000 ohms. If I am not at a half wavelength, it's going to be less than 4,000 ohms, maybe 3,500, maybe 3,200, maybe 2,500. So it'll be less than 4,000, but not low enough to be 50 ohms. So then I have my 9-to-1 transformer. So let's say, for example, my random wire antenna is about 2,500 ohms. With a 9-to-1 transformer, on the radio side, that impedance is going to go from 2,500 ohms down to about 400 ohms, roughly. So, okay, that's a whole lot closer to 50 than 4,000 was. So now if I have a tuner, I can tune that much of a difference. So essentially what the 9-to-1 does is it gives your tuner a running start in the impedance conversion down to the 50 ohms the radio wants to see. Most radios today that have built-in tuners have tuners that tune a fairly limited range. They typically are what they call a 3-to-1 tuner because it'll go from about 16 or 20 ohms on the low end to about 150 ohms on the high end, which means if your antenna is close to resonant, it'll trim it okay, but it won't like tune a bed spring. It's not like going to tune any random thing you're hooking up to. So usually for that, you either need a radio that has that in it, and a few do, like Elecraft, KX2, KX3, K3, K4. They have very wide range tuners, but most ICOM, Yaesu, etc. radios have a 3-to-1 tuner. Now you can get many commercial external tuners from companies like LDG or MFJ. Used to be SGC. They're out of business, I think, at this point. So all the 3-letter companies make tuners. So these guys all make random wire tuners. So when you buy a tuner for this kind of antenna, you have to make sure it's a wide range tuner. Take an LDG tuner, for example, an LDG Pro Z11 Pro 2 tuner, typical tuner. That has a tuning range of about 20 ohms to about 1,000 ohms. So it's got a pretty wide range. It's not wide enough to handle a random wire without the unknown, without that 9-to-1 transformer. But between the two of those things together, it works great. So that's how you get the impedance down to 50 ohms, which is what your transmitter wants to see. The other question, the problem that popped up was like, what happened to the counterpoise? What happened to the other half of the antenna? And as my good friend Kirk says, RF got to go somewhere. So it doesn't just disappear. What's happening is as the RF goes from your transmitter to the feed point, And imagine the piece of coax. There's a wire in the center of the cable, and then there's a shield around that wire. The electrical potential, the RF energy, is between the inner conductor and the shield on the inside of the coax. So it's the outer skin of the center conductor and the inner skin, if you will, of the shield. That's where that potential is. And it travels up the coax till it gets to the feed point, and then it's going to be radiating. And it finds one element, but it's lacking another one. So what happens is those RF currents will whip a U, make a U-turn, and they'll start coming back down the coax on the outside surface of the shield. So what's happening here is, even though you didn't tell it to do it this way, the RF is going to be going partly to the radiating element, and part of it's coming back down the coax, heading for you and your radio. Well, is that a good thing or a bad thing? Well, it depends. Like virtually every engineering answer is answered with the phrase "it depends." So what is the "it depends" part? Well, if you're operating QRP 5 watts, that amount of current is pretty low, and it's probably not going to cause you any problems. If you're operating a 100-watt radio, a lot of RF current coming back to you will cause the radio to shut down or get interference into some other thing in your station. So it can be a problem. There's ways to mitigate that, but that's the problem. So how well does it work? The answer is it works pretty well if you can not interfere with the gear that's generating the RF. It actually works reasonably well as a counterpoise. Is it as good as having another radiating element up in the air? Probably not, but it's good enough. Good enough for portable work for the convenience of that. So that's basically how a NFED, and specifically a random wire NFED, works. So the way to get rid of that RF that heads back to your radio is to put what's called a choke in series with the feed line. So if you run, let's say, 20 feet of coax from your radio to the feed point, and you're getting RF coming back to you, if it's 5 watts, it's probably not a problem. If it's 100 watts, it's probably going to be a problem. So what you want to do is intercept that, and if you can, somewhere in the middle of the coax, put a choke in it. What that will do is it'll prevent that current that's flowing back down the coax from getting to your radio. It'll actually attenuate it so much that it's essentially negligible. Where should you put it? Well, you want it far enough away from the radio to not interfere with the radio, and far enough down the cable from the antenna to give you a counterpoise. So my personal advice is, however much coax you've got, if you can stick it in the middle, that's a good place for it. So when I operate portable high power, what I'll tend to do is go from the radio to the choke with about 10 feet of cable, then from the choke to the antenna with about 20 feet of cable, and then there's the radiating element. That gives me a 20-foot counterpoise, but it's 10 feet away from my radio, and that works great. Never had a problem with that. Now, the other thing you could also do is you could add a counterpoise wire at that 9-to-1 feed point. In fact, on our antennas, we have little sockets where you can plug in a wire and add a counterpoise to give you more of a ground. And this is the third most common question I get, does it make a difference? In my personal experience, no, it really does not make a bit of difference, and I wouldn't bother. Now, your mileage may vary. You may find it useful in some circumstances, maybe due to what you have around your station, et cetera, but it's really not worth the bother, honestly. The coax works perfectly fine. Let's talk a little bit about the other kind of NFED antenna, the NFED half wave. Now, an NFED half wave is different from a random wire antenna in a huge way, and that is, it is actually a resonant antenna. It's cut to be a half wavelength long for the desired band, and you do not need a antenna tuner. The actual length of the wire will be slightly less than a half wave, mainly because there's a 9-to-1 transformer at the feed point, and that inductance allows you to shorten the antenna a tiny bit without, I mean, I'm talking like 5% shorter, not like half. So it's a teeny bit shorter. The 9-to-1 transformer will take you from that 4,000 ohms down to 50 ohms quite directly. And the way you tune this kind of an antenna is just by adjusting or snipping off the length of the wire itself till it's resonant at the point where you're going to operate in the band. And it's pretty broadband. If you cut this kind of antenna for the middle of the 20-meter band, it'll work the whole 20-meter band just fine with no changes required. The same rules apply as the random wire with regard to choking. So if you're running low power, 5 watts, maybe 10, maybe if you're lucky 20, you can get away without a choke. in the feed line. But if you are operating high power, then you might need a choke. Again, the coax is providing part of the antenna. It's providing the counterpoise to that half-wave antenna. So what does a choke look like? This is an internal view with the wrap pulled away. It's simply a big ferrite that has some coax that loops through that ferrite. Every time you run a piece of coax through the ferrite, it is essentially doubling the inductance of that that choke. Now, just as a little aside, a lot of times when people have RF interference problems, they say, or their buddy says, "Look, just get one of those snap-on ferrites, snap it on the cable, it'll be fine." Maybe, maybe not. Why is that? When you put one of those ferrite cores on the cable, it will cause a little bit of a impedance or resistance, if you will, from the common mode current flowing through the cable. If one is not enough, you can snap on 2 or 3 or 4 or 5 on the cable. What happens is every one you snap on there increases the inductance by whatever that core is. Let's say that core gives you 100 ohms of impedance. If I have one, I get 100 ohms. If I snap on 5 in a row, I get 500 ohms of impedance. I never do that. The reason is, what you really want is a lot more than that, a lot more than 500 ohms of impedance. You want like thousands of ohms of impedance. If you take a core, you pass the cable through the core, that's the same as one of those snap-on beads. If you take that wire and wrap it through the core a second time, that 100 ohms of impedance becomes 200 ohms. If you pass it through a third time, it becomes 400. If you pass it through again, it becomes 800. If you pass it through again, it becomes 1600. So you essentially are doubling the impedance every time you loop the cable through that same core. And on all of my RFI elimination exercises, I always loop the cables through 5, 6, 7, 8 times because I want to choke the daylights out of that cable to keep the RF out. This is a great tip, by the way, for things like USB cables from a computer to a radio. A lot of times, the most sensitive thing in the station is the computer. If you have a computer hooked to your radio to do digital modes, for example, the first thing that's going to get affected is that USB connection from the radio to the computer. Choke the heck out of that cable and you can solve your problem pretty easily. So that's the same thing that goes into the choke inline in the antenna feed line. All right, let's talk about building a transformer. I said these things are pretty easy to build. You can do it yourself. You can get yourself a core and some wire and make a transformer. Now, a transformer is merely windings of wire on the core. In like a one-to-one transformer, the number of windings on the primary and secondary are the same. If you want to change that impedance ratio from 1-to-1 to, let's say, 1-to-9, then you wrap a different number of turns on the primary versus the secondary of the transformer. So what you see here in this little illustration is there's 2 wires, a red wire and a black wire. The red and black wire are common at point A, which is the B and C connector. And then both wires they're twisted together and they're wound around the core twice until the red wire goes to point B. And then the black wire continues around another like 12 times until it exits the core. So what you've got is a big turns ratio difference. You have 14 turns versus 2 turns. So that provides you a transformer. That's the impedance transformation. And so you can see here, if you have 7 turns ratio, 2-to-14, that's 7-to-1, that is a 49-to-1 impedance transformation. So if you present an antenna to that core where that wire exits, right there, if that's, let's say, 2450 ohms, you'll have exactly 50 ohms on the other side, which is what your radio wants. Now, you can change the number of turns, you can change the length of the antenna. Both of those things will adjust the tuning. Changing the wire length of the antenna usually is the easiest of the two. And so that's how you tune those kind of antennas. Very simple to do. This is a picture of what the prototype looks like. This is a long, long time ago, but it does give you an idea what you could do with it. So with such a simple 49-to-1 transformer, you can see on my fancy MFJ antenna analyzer that in the middle of the 20-meter band, the match is flat. It's like 1-to-1. Which is ridiculous. I mean, all commercial antennas you buy are rated at 1.5-to-1 or better. So if you tune an antenna properly, most of these antennas will give you a 1.1 to 1.3 SWR, which is well below what you really need. 1.5 to 1 is considered very good. So this is the beauty of a resonant antenna. Now, by the way, if you were to graph the response curve of that antenna over the whole band, let's say over all of 20 meters, what you'd find is that the sweet spot, you can get a very, very low SWR. At the end of the 20-meter band, instead of 1.2 to 1, it maybe it's 1.4 to 1 or 1.5 to 1. So it's really, really good. And that's brought to you by full-size wire. There's no magic that we do. It's just the nature of a full-size antenna and why we think they're so important. Okay, we talked about that mast quite a bit. Here's some photographs of how I like to deploy. This is a carbon fiber mast. This is not the fiberglass one, but the idea is the same. A lot of places that I operate, sometimes there's grass, sometimes there's not. And so I tend to set things up with a tripod. So I take a lightweight carbon fiber photo tripod, remove the photo head on the top, the ball, take that off. Usually there's a stud that sticks out the top of a photo tripod. And so I made a little bracket that'll slip over the stud with a wing nut, and that will hold the mast at the top. And then there's a piece of Velcro that holds it at the bottom, and it works great. If you have any wind, you don't even have to stake it. I have a little red bag that's got about 5 or 10 pounds of weights in it, little hand weights, with a little piece of paracord that slips over the hook on the tripod that essentially pulls the tripod to the ground, and it's not going to fall over. It'd be a pretty nasty wind if that thing fell over. So this is the low impact, super easy way to set up an antenna anywhere, even concrete, asphalt, whatever. And even if you take it to a park, if they won't let you put a stake in the ground, like a national park, then you could use this method. I'm a big fan of lightweight, as you can tell. So this is a carbon fiber tripod, super lightweight, very compact. You can even use it as a photo tripod if you screw the head back on. So that's an extra bonus. This is what that little bracket thingy looks like. And that's it mounted. So very simple idea, very lightweight. And then to hold the wire to the mast, when I first started doing this many, many years ago, I just took a rubber band and just rubber banded the tip of the wire to the tip of the mast, and it was fine. But since then, I've playing around with a bunch of different ways to do it. So I tend to put a little fishing swivel on the top of my mast. And this way I can clip one of those little plastic carabiners, or I can run a wire through it, or whatever I want. It's just kind of a universally convenient way to attach the end of the wire to the mast. Sometimes I'll just take the wire and make a little loop, tie a little loop on the end of the wire and just hook it in there, and that's fine. All the mast is doing is holding up the lightweight wire. It's very easy. So there's the weight bag. And if you want to guide out, you can also just stick a little guy ring over the mast. This is another thing that we made a couple years ago. It's a 2-meter antenna. So a lot of guys are doing SOTA with on 2 meters. And many want to actually run 2-meter single sideband, which I love doing myself. Single sideband is historically horizontally polarized. And if you take something like an 817 or a 705 to a hilltop and you want to run sideband, you need a horizontal antenna. And so what you can do is take this little feed point, you Velcro it to the mast, and then you can take two 2-meter antennas and just snap them on either side. Now you have a horizontal dipole, and it works great. It was designed to work with Comet BNC 24 antennas. You can buy them anywhere, and just plug them in, and it works really well. You can also disconnect one of the dipole ends and pop it on the top, and now you have kind of a half-baked ground plane. So you have a ground plane with one ground radial. So you can use that on FM, or you can do it horizontally like you see here for a single sideband. So by the way, here you could even see on the analyzer where it's 1.15 to 1 at 145.6. And if you move off frequency even quite a bit, you're still well under 1.5 to 1. I mean, that's, again, even at VHF, a full-size antenna makes a difference. So that's pretty much it. So here's kind of my maybe a little guideline around which antenna is the right one for which radio, for which reason, kind of summarizing it all together. So if you have something like a Elecraft KX2 or KX3 that have a wide range tuner, which are wonderful radios, then the end-fed random wire antenna is ideal because you can just change bands and it'll just work. You don't have to do a thing. Once you set it up, you're on all bands immediately. If you have something like a 705, a Lab 599, FT817, FT818, kind of radios that do not have tuners built into them, you can always have a tuner externally, but if you don't, then the end-fed half wave or inverted V is a better choice because they're resonant. You don't need a tuner. So I would say the most popular for QRP portable for these radios is the end-fed half wave. And then the higher power radios like an 891, 7300, whatever, 50 to 100 watts, then the inverted V or end-fed random wire, well, if you have a tuner. 7300 weirdly kind of has a tuner built into it that goes past 3 to 1 at 50 watts. So that's a useful tidbit. Anyway, that's it for the recommendations, and I'd be happy to take any questions.
Great question. Sounds like crickets around here. I guess
Are you all still awake? Just checking.
I think you.
Thank you.
Pretty good. We appreciate you. Hang on just a minute. We got one.
One question. Can you hear me all right?
Yes.
Okay. The choke that you use on your feed, does it affect the outgoing transmission as much as the feedback transmission that you're trying to?
No, it's totally transparent to the power going forward. It just passes right through.
Okay.
It only affects the common mode current that's flowing on the outside.
Okay. Just thought I'd ask that.
It's really a piece of magic. I mean, it's a super simple thing that does an amazing job.
Yeah.
All
Okay.
right. So
Anything else?
I'll throw in one kind of question and comment. George, now that you've kind of retired from National Instruments, you're spending a good bit of time with Pac-10, and I guess you're still doing controllers and that sort of thing. Do you see growing that company? I don't want to put you on the spot, but is that something that you envision doing with Pac-10?
Probably. So I'm constrained by my wife encouraging me not to give up one job for another job. So I appreciate that. Yeah. So we took kind of we kind of had a bit of a lull in the action over the previous year because with the moving and I was traveling a lot for work and all that, it was really hard to keep the business running and fulfilling orders wasn't so bad, but frankly, keeping stuff in the manufacturing queue is a pain. So a very good friend of mine, actually ours, Mark N6MTS, who has his own company called Halibut Electronics, offered to take care of order fulfillment for me, which has been really great. So I get all the orders, and so if there's any business issue, I take care of it. But if there's any, and I work with the manufacturers, the assembly houses to build the antennas, but all the actual order processing then goes to Mark, and he fulfills the orders. So that's good for him and good for me. So it's been a great partnership, and so I think we will probably wind up getting back to the point where we have a pretty consistent inventory. We've been doing a whole lot of making a batch and selling them out. Here's a dirty little secret. The dirty little secret is that from the time I started doing this, I thought, well, who wants this? And I know I do, but like, is there anybody else who wants this sort of thing? And so I would make a batch of antennas, enough to make it financially viable, but not more than I thought I would sell. And then I would sell them out. And then I'd make another batch and I'd sell them out. I'd make another batch and I'd sell them out. And you'd think I'd learn. But I've always been a little leery of like, I don't want to make too many of these things because I don't want to like own 1,000 of them and have nobody want to buy them. But it always is turning out that no matter what we make, we sell them out. And so that's really wonderful. I mean, that's a great problem to have. And so I think we're starting to make bigger and bigger orders to our manufacturer. By the way, so we do all the design work ourselves. We buy all the parts. So we control all that, and then we ship all the parts to an assembly house, and they do the assembly of the finished units and send them back to us. And it's done in one of two places. It's Oak Park, Illinois. Shocking, you thought I was going to say Shenzhen, but the primary antenna construction is done in Illinois, at a contract manufacturer, really big CM. And then a lot of our circuit board assembly for other products, not antennas, but for controllers, are done by a company in California, in Monterey, California. So we don't do any offshore assembly. You can't. A lot of the parts you have to buy from China. I mean, most of them actually I buy from DigiKey, but half of them are made in China. But the assembly we do all here in the U.S. So anyway,
Well,
long story short, there, Frank.
Yeah, no, I appreciate the context of that. Those in the audience who have started their own business will already know what I'm about to say. I've worked with, I mean, literally over 100 small businesses of a variety of technology niches, software and others. And the biggest problem is early success. Now, gosh, why would that be a problem? Well, because you immediately sell out. And then the secondary reverberations of, I've got to have a pack antenna. You don't have one? What's wrong with you? And so the problem with that is you've got to invest a fair amount of money. And there are oodles of manufacturing companies that put their stuff on QVC TV to sell for pennies on the dollar because they overbuilt relative to a good guess on the market. So, well, I will tell you this, and I truly mean this. I've said this to George before. I know of no ham radio company, bar none. And when I walk in MFJ, they actually know who I am. So, I mean, I get some pretty good service there. I don't know of any company that has as good a customer service as Pactana, and it's because of George. And George could make a higher profit margin if he wasn't such a good customer-oriented manager. And I'll compliment him that way. So if you have any ideas about purchasing there, the biggest problem you'll have is, gosh, our stock is in production. It'll be next month or whatever. But George, I'm sure he's lost money by making sure customers are happy. So I'll just sort of end with that. And I just wish you well. A person I love dearly, he's passed on now, George. He told me not to retire from something, but retire to something. And that's, but I appreciate your wife, who always knows best. Yes, dear is a common phrase in my household. Retire from one job to another. So you do it the way that fits best for you. Because I got into building infeds because George is out of stock, and I went, well, I don't really know a bunch about it. Let me read, and I truly love cutting those wires and tinkering with the counterpoints to get them just right. Those in the Vicksburg Club know my good friend Thomas Gandy, N5WDG, wide area engineer with a company called AT&T. He would not believe that I got it down to 1-to-1 on an 80 meter, a long one. And he asked me, who the hell taught you to use that MFJ antenna analyzer? Do you know what you're doing? I said, well, the guy who invented it taught me how to use it. So anyway, I'll leave that there. So any other questions from everybody?
Yeah, I've got one.
Jerry Ash has got one.
I've got a random length wire to the 9-to-1 balance, and I built a metal stand to slide it into the receiver hitch on the motorhome. Does that make the frame of the motorhome a counterpoise?
Yeah, if from the radio to the feed point to the matching unit, there's a piece of coax, right? And is there a connection to the body of the truck there at the hitch, or how does it connect to the body?
Well, it slides up into the receiver hitch.
Yeah,
got a ground wire also hooked to it.
Okay, yeah, if you have a ground wire from, if the matching unit is here and somewhere on the matching unit there's a ground point, and then that goes, let's say, with a piece of braid to the body of the car, then for sure you do. If you're relying on just the receiver working as a connection, it's not really meant to be electrical connection, and they're painted over usually. So I don't know, but probably it is becoming that. Now, one thing that I'll add too about these end-fed antennas, the tuning of an end-fed antenna is related to a whole bunch of physical factors: the frequency you're operating on, the length of the wire, the length of the coax. I mean, and all that stuff's pretty obvious, but it's also somewhat dependent on the elevation of the feed point above the ground, where the end of the wire of the antenna is, and objects that are close by, including the body of the truck or anything else that you happen to be parked next to. So the tuning could be varied, depending on the stuff around there. So anyway, long story, answering your question, is the body becoming the counterpoise? Yeah, if there's some kind of mechanical connection between the ground of the coax at some point and the body of the car, yes.
Okay.
Very good.
Anything else? Nothing? All right, I think that's it. We appreciate it.
All right, thanks very much. I appreciate you having me. Thank you, Frank.